All right, so I think we've done a good amount of time on that. So I've got a question. How terrible was the timed lab this time around? What? It was pretty hard. Relatively hard. People. Okay, so the two problems that I gave you. So for the two tree problems I gave you, specifically the tree ones, those are about the difficulty that I don't consider those necessarily too difficult once you've seen them a couple of times, right? But questions it's very hard to create questions that are like that, but harder or easier, right? Those questions are those questions. They will just simply be very similar. And if you look at the practice exam, which I will probably go over on Wednesday, the questions on the practice exam are very similar. Now, somebody else asked basically, what other stuff is going to be on the exam? Like whether or not you're going to have to worry about. Seriously, did I just? Okay, so colon that size, keep changes, and then over here on the primary, no, I want to use 150. Okay. So and then the other question was on the exam, on the actual exam, how much is there going to be on maths and sets? And the answer to that is exactly as much as on the practice exam, which is one 10-point question. And then also, right, I'll just open up the practice exam for a second here. So teaching, destruct, exam 2. Come on, practice. There we go. So here, right, so here what we have was a bunch of data structures where I had you to choose the best one. On the exam, I'll ask you to also, I'll also ask you to give me like a 1-sentence justification, just so simply that if you choose the wrong answer, maybe you can argue yourself a lot of partial credit that way. But basically, right, set or map, you can expect basically like similar questions on the actual exam, and give me something like that. But most of it, as you can see, refers to trees, like know your tree, give me the tree vocabulary, right? Know what a complete tree is, a perfect tree is, a full tree, right? Give you those here, draw examples of those. This is a classic question I give on the exam. Draw the binary tree that you get after you insert stuff. It's going to be the exact same question on the actual exam, just different numbers. Delete instead. For delete, I will give you a tree, and then I'll ask you to delete stuff from it, right? I think will be worth more points on the exam. Heap. How does the heap algorithm work? Describe in detail. How does it adding to a new element work? So on the exam, instead, they're worth the same amount of points, but instead, I'm asking you to do essentially the same thing for a binary that I did for a binary search tree, which is please add these things to a heap and show me the resulting heap, right? And remove these things from a heap and show me the resulting heap. And hopefully that heap portion of the timed lab wasn't too hard, right? That should have been fairly easy. Like there were a bunch of free points in the whole here's the formula, do the formula. By the way, check the slides. They have the code in them, right? That kind of deal. So it wasn't meant to be too hard. It was meant to be basically if you remember that you have resources available and you use those resources wisely, then you can use them. Huffman tree, here's a frequency table. Draw a Huffman tree for these symbols, and then encode the string. I'll probably give you a decoding problem on the exam. And then these coding problems, write a method which, given the tree of integers, computes and returns the sum of all the integers stored in the tree, right? That's about the difficulty of what you could expect on the exam. To be honest, I do have something that's in between these two difficulties, the equals and the sum tree. I have a problem on the exam that I like because it actually showed up in real life back in 2016. But for the map, did I? Yeah, I didn't. Returns the characters which occur in a string and how many of them. That should have been, okay, so that's wrong. That should be string s, right? That should be string s rather than int n, right? Because return write a method that which returns which. Wow, I really messed up writing there, but that's what happens when you're trying to code and there's a bunch of screaming children all around you. But basically, there's something of this nature where you have a map of characters to integers, where you're just counting the number of characters that appear in a string. And just know some basic analysis, like ask yourself, what does the Huffman tree look like if all symbols are equal? What are the worst cases for inserting and deleting in a binary tree, and why? What is the best case? What is the average case, and why? So those stuff. So come back with those questions answered, and you should have no, and I'll go over them on in detail on Wednesday, and you'll have no problem on the exam. You'll notice that there's not too much coding on this exam. A lot of it's theory. A lot of this exam is theory. That's why, and yeah, the code's a significant portion. You're going to do poorly if you can't do the code, but at the same time, it's pretty easy. If you know what you're doing, you can get some good credit on the code. So what we're going to do today is that we're going to finish up hash tables, because I had only like one little bit of hash tables left, right? We've already done quite a bit today in about 20 minutes, going over the homework, going over other stuff. But right now we need to do two things, which is I've been saying stuff is constant time for hash tables, and I kind of haven't I just said that and not actually like kind of prove that in any way, shape, or form that's acceptable. That is not what I needed. That was, here we go. So I mentioned quadratic probing, right? So I mentioned in my video that there's two types of probing. There's linear probing and quadratic probing, right? We've been dealing with open addressing in the videos that I've talked about, where basically you just create a hash. When you get a collision, how do you deal with collisions in a hash table? You just simply look for the next available space. Quadratic probing was, well, rather than looking for the next available space, because that's going to create clumps, like something's going to collide, so it's going to look for the next space, and then we're going to get another collision there, so we're going to look for the next space. Rather than looking for the next available space, I'm going to look one space away, so the next available space, then 4 away, which is 2 squared, then 9 spaces away, and that will lead to having more gaps. But of course, if the hash table is really full, you can imagine that you could go much longer without actually hitting the space you need to land on. So, but those are just two different strategies that deal with open addressing. And there's a bunch of other strategies out there. But the other primary strategy is chaining. It's the alternative to open addressing. Like, it's completely possible that one semester we do open addressing and focus all the way everything on open addressing and writing and coding up open addressing. The other alternative is like focusing on chaining. And here we're just going to barely mention chaining because it's a very easy concept to understand. Rather than having an array of entries, right? Rather than having an array of key value pairs, instead each of these is a linked list over here. Each of the slots in an array, instead of holding one value, it's a linked list of values. We sometimes, instead of calling these things linked lists, we'll sometimes call them buckets. And essentially, the way you deal with a collision is you just simply add it to the end of the linked list that you collided with, rather than looking for another available space. Now, the pros of this is that it's really easy. You don't have to like do any rearranging of the math or anything. You don't have to do anything like that. The disadvantage of this is that if a linked list gets too long, of course, then, right, if everything collides into the same bucket, then essentially you've turned your hash table into a linked list, which doesn't do anybody any good, right? But so long as we keep our heads and are smart about this, we're good. Advantages to open addressing, right? Once you hit a bucket, you only have to look through the values in that bucket. You don't need to have to worry about like those weird deleted entries that I had to do for open addressing. You have to resize your table a whole lot less because a bucket can hold a lot of things in there. And once you determine an item's not there, you just simply add it to the end of the list. Okay. So there's no tricks here. You just simply add it it works exactly the way you think it should. You add it to the linked list or you move it to a linked list, and it just happens to be a bunch of linked lists. So how do these things work in constant time? Well, what we've I've mentioned this obtusely a couple times. We work off of the load factor. So that's the number of filled cells divided by the table size. In other words, how filled up is this? Right? For using chaining, because you can have more stuff in the table than the actual size of the table, that might be more than one. But for open addressing, obviously, that's just the percentage of slots that are filled. Okay, and that's the greatest factor. It's the whole parking garage comparison that I'm talking about. If your parking garage is half filled, it doesn't take much time to find a space. If it's 90% of the way filled or 99% of the way filled, or there's all but one space filled, it's going to take forever to find a space, right? So the lower your load factor, that means there's less stuff in there. And logically, that means less chances of collision. So it's going to work better the less stuff you have in there. If you don't get a collision, it's constant time, obviously. You just insert into the table at the appropriate slot. But then what if you have collisions? How long is that going to take if you have collisions? Well, fortunately, Knuth, who's like the uber genius of computer science these days, who has written like multiple tomes on computer science, they're like amazingly like complex and thorough and stuff. He derived a formula that says, okay, here's the number of comparisons, the amount of basically checks you have to make to find a hash table, to find an item that's in a hash table using open addressing with linear probing and has a load factor of L. So this equation says that if it's L filled up, so like 0.75, so if it's 75% of the way filled up, this is how many collisions you're going to have. So let's go ahead and work that out. And this is on average. On average. This is the expected number, right? Assuming that you don't have, terrible luck like that, space station that just burned up. So assuming you don't have the luck of one of those pieces crashing on your head, and this is the kind of answer you're expecting. So collisions is equal to 1 divided by 2 times 1 plus 1 over 1 minus, whatever the load factor is here. So we're saying that our load factor here is 75% of the way filled up. So let's assume that our hash table is 75% of the way filled up. So 1 minus 0.75. So that should be 0.25. So 1 over 0.25, that's 1 over 1/4, which is what? 4. 4. 1 plus 4 is 5. Divided by 2, so 2.5 comparisons. Let's see if that jives with the answer we have on the table. Yep, 2.5 there. Okay, so if it's 0% of the way filled up, by the way, right? 1 over 1 minus, so 0% of the way filled up. That goes to 1, so it's 1 plus 1, which is 2, divided by 2, which is 1. So if it's 0% of the way filled up, then you've got one comparison to do, right? Not because you're checking the space. That's a comparison. You're checking the space to see if it's filled, right? So that's one comparison. But if it's 75% of the way filled up, then you expect to have basically between 1 and 2 collisions, right? And then you check the third space and see if it's that second or third space and it's full. So that's and notice that this is the load factor. This is the percentage of the table that's filled up. This isn't, right? This is the percentage of the table that's filled up. What's not in here? N. N is not in here, right? This is the size of the table is irrelevant. This has nothing to do with the size of the table. And because it has nothing to do with the size of the table, so basically this is the expected amount of time this should take, regardless of size. If you're using chaining, then on average it's basically, using chaining, if the item's in the table, on average you have to basically you look at the bucket that all the items are in, and then you go through, then you search that linked list, and so how long does searching the linked list take? It takes basically half the linked list on average, right? So you search through half the items to find it on average. So how big is each linked list? Well, assuming they're evenly distributed, then it's whatever the load factor is. So basically, if the load factor is 5, right, that means then each bucket has 5 items in it on average. So the average amount of time it takes to find something is 3.5 comparisons there. So L is the average numbers of items in a list. So the number of items average number of items in a list. So that's kind of like your load factor there. So if we look at that for open addressing with chaining, and so linear probing. So if we've so remember how I set mine, I think, to 75%. That meant with my hash table, I'm expecting to basically 2.5 checks no matter how big the table is. If I had let it get up 90% of the way full, that doubles it to, I have to check 5 spaces before I find my parking spot. And if I get to 95%, that's 10 spaces maybe before I find my parking spot, right? I find it on average on the 11th try, which is still a lot of checks over there. But it's a constant number of checks, especially when you're talking about maybe 1 million items in that table. So is this better or worse than log of n realistically? Because constant time is theoretically better. Constant time is always theoretically better. In practice, does it, how does it compare? Right? So if we're searching, so remember what it takes for searching an item in a binary tree. It takes log n time to search a binary tree. A sorted array of 128 is 7 probes to find an item in a binary search and sorted array. Or it would also take 7 checks in a binary tree to find something that has an item in 128. Sorry, 1 item out of 128 items. That's more checks than any hash table that's more than 90% full. That's more checks than basically all of these things. So if my hash table, so long as my hash table is like less than 90% or less full, it's going to take, the hash table is going to run quicker. But what's the disadvantage of using hash tables? One, you can't keep sorted data in the hash tables. Right, if we're looking for sorted things, well, we can't. That's really comparing apples to oranges here, kind of. And the second thing is that, of course, we're sacrificing space to the time gods here, right? The gods of time have deemed us that we can have a constant time comparison, and we are just sacrificing our computer's memory so that we can get that. We are sacrificing oodles and oodles of space, right? If I have 1 million items in my hash table, right? If I have 1 million items in my hash table, if I have, let's say, 750,000 items in my hash table, that means if I'm letting my load factor be 0.75, that means that there's 250,000 wasted spaces. That's a lot of wasted space, right? If you're using up 750 megabytes, you're wasting 250 megabytes, right? So 75% of the space is used, 25% of the space is unused, right? Hash tables eat space alive, but space is cheap these days. Well, unless you're trying to build a gaming rig and trying to buy RAM, which is in short supply these days because all of it's going to phone manufacturing and you can't build a computer these days. I know, it's very sad. But relatively speaking, space is cheap, especially when compared to time, because remember, you can buy space, you cannot buy time. Okay? So that's essentially it for hash tables. The big thing to note here, though, when I say constant time, right, these are expected checks. These are on average. Worst case scenario, with the bad hashing method, and in something where I showed in the video where you can have where basically things are not evenly distributed. In fact, part of my dissertation was showing that some very common cryptographic hash functions that say they're going to evenly distribute stuff don't actually evenly distribute stuff all the time. It gets it can get longer. That's why a lot of people like to write maybe that the expected runtime for these things are constant time amortized. Because occasionally you have an O of n step where you have to resize the table and rehash everything, or that basically, well, there's a big asterisk over here because also worst case scenario with those bad hashing functions, you might actually be getting something that's more like O of n time. But a lot of times hash tables work because you're working with strings and integers, and those hash really, really well. And again, what are hash tables really good at? Hash tables are really good at counting things, like counting the number of characters in a string, counting the numbers of each word in a document. So doing what we wrote the index tree to do, essentially, and categorizing, right? Creating a bunch of categories, and then creating a list of the things that belong in those categories. That's real. This is what they're really good at: categorizing and counting, which is a surprising number of computer science problems. If you want to get more practice with hash tables, I don't know when these came up, but it is under new. There are map 1, there are problems that use get input for hash tables on coding bat. So there's some good practice problems over there to use them. I also somebody noticed that there was a hash table in Java, and we've been teaching hash map. Hash table is a bit older, if I recall, but you can probably use either, but use hash map for right now. Oh, generally the default load factor 0.75 offers a good trade-off between time and space costs, right? So look up them both and see which ones you need to use if you're actually like using a project. Like hash table is good for synchronization, but otherwise, there's not really. But really, there's not too much of a difference for your uses in the class. So just focus on using hash map. If you accidentally put hash table down, oops, whatever. It's not a big deal. Okay. So, all right. So that's really what I've got on the hash tables. Now, what are we going to do for? So what are the last 2 chapters we have? Well, we have one more data structure to learn, which is graphs, and that's chapter 10, and I like saving that for the end. And is everybody feeling like kind of just super pressed for like a lot of work right now and a huge amount of stuff, right? So we're going to move on to a much easier chapter now. So one that doesn't involve data structures, right? And the assignment, I don't even know what we're going to do for this assignment. We'll see what we do in lab. I've tried different assignments. A lot of the assignments I've done in the past are pretty easy for this one coding wise, right? Because essentially it says copy the code out of the book and make some modifications, and they end up being boring. So I'm looking for something a bit more exciting, but if I don't find one, whatever, right? This one's a bit of an easier chapter. So now some of the stuff that we learn on here will be in the final exam, specifically merge sort, insertion sort, and quick sort are on the exam, but we're going to learn about sorting, okay? So we are going to learn a whole lot of sorting algorithms here. And some of them I'm not going to bother teaching on the list. And sorting algorithms are really, you should have learned some sorting algorithms. So anybody, tell me a sorting algorithm you learned in 1068 or before, or in a class, in another class. Anybody? Selection sort. Okay. Selection sort. That's on there. Anybody who learned something else from this list? Bubble sort, right? We're going to relearn those. Don't worry. So I'm not going to assume that you've learned any of these because I'm actually partial to insertion sort, and we're going to learn the reason why I love insertion sort today. In my opinion, insertion sort is one of the best algorithms out there. Shell sort, I'm probably going to skip over, but so these 3 you can learn essentially without much trouble. Heap sort requires you to understand how heaps work. So go figure with that one, right? So no wonder that you're not going to learn that in 1068, even though it performs much better. But the other 2, merge sort and quick sort, they require recursion. So this chapter can come right after recursion, but this is a data structures and algorithms course, and I really like, or a data structures course, and I really like the emphasis on data structures. So I like this over here because this is when normally the meat, kind of hits the grinder, and you've really got to, work on stuff. So sometimes an easier chapter right over here helps with students. So we're going to learn about these algorithms. We're going to so we've learned about, and we're going to learn our 5th big O notation that's commonly used. So we learned about constant time, linear time, and quadratic time, right? First. So we learned about those times and what those felt like. We also learned about log n time, so logarithmic time. So now we're going to learn about log linear time, which is n log n. So, and that's what the better sorting algorithms run at. So, of course, first we want to formally define sorting, and that's essentially putting items from smallest to biggest. That means that the items have to be comparable, of course. For simplicity's sake, we're going to be dealing with integers, but you can write it if you write a generic sorting algorithm, one that works on generics that are comparable. You can write a sorting algorithm once, and it's going to work on everything. Knowing how sorting algorithms work, it's important. And in programming, and say you're taking a programming interview, if you recognize that, one of the first things is will sorting help me here? And that gives you kind of an upper limit to the problem. If I sort this thing and go through it one item at a time, I can solve the problem, right? So sort it once, that takes n log n time, and then go through it, that's O of n time. Then you have an upper bound as to how long this problem should take, right? And you can get an answer even if it's not the best answer, and then you can think about a different approach, because then at least you can say, I've solved it, but I know it's not the most optimal thing. So we're also going to learn the strategy of divide and conquer, which is a recursive problem-solving strategy. And this is also good because we're going to learn a bunch of different algorithms that do the same thing, essentially. That all basically, they do the same task, even though they do a different way. So Java provides an arrays class, which uses .sort. Collections has a .sort for sorting lists. It says sorting methods use quicksort for primitives, and then merge sort for objects. I don't think that's true necessarily anymore because timsort came out and changed everything. So there is and I haven't seen that taught in classes yet because it's that new, and by new I mean it came out in 2002. Wait, no, 1993, and it was implemented in 2002 in a programming language. Okay, and that one's a hybrid merge sort, but a lot of these, yeah. So it was used to sort arrays of non-primitive type in Java SE7. So it's been used in Java 7. And it was a bug thing. We replace merge sort with timsort. So timsort is pretty cool. You should check it out, but I'm not necessarily going to be able to go over it. But Java already has, your programming language has a bunch of sorting algorithms built into it, right? It's got arrays. You can sort a bunch of items. You can sort a bunch of objects between two. You can sort a bunch of stuff between indices. You can sort a bunch of items that it doesn't know how to compare by providing a comparator. What is a comparator? Well, say you provide something that you did not implement the compare to, but you think it can be sorted. The comparator is an object you can pass in and says, this is how you compare two things. But essentially, there's stuff that's built into doing the sorting. And most of my we're gonna assume that when we're sorting stuff, we use this declaration. Public static, we're sorting a bunch of t's, which are a bunch of comparables, and they're appearing in a list. Actually, when I'm right on the board, it's just gonna be a bunch of integers. So it doesn't really matter. So we're going to start out with the most terrible sorting algorithm of all. The most terrible usable sorting algorithm of all. There's plenty of worse sorting algorithms on there. Selection sort is actually usable, so it's the worst of stuff you can actually use, I guess. So selection sort, though, is very easy to understand, which is why we like starting with it. Essentially, you go through the array a bunch of times, and you take the smallest item in the array and put it where it's supposed to be. So in other words, I go through the array once. On the first time I go through it, I go and look through the smallest and put it in the first index 0. Then I go through and look for the second smallest item and put it in index 1. Then I go for the third smallest item and put it in index 2, and the fourth smallest and put it in index 3, and so on and so forth until the entire array is sorted. That makes sense? You're just looking for the small. Essentially, imagine you have two. We're going to do this in place, but imagine you've got a pile of, a pile of, say you're a TA, right? And you're sorting. And you want to sort the class's paper by last name. So you look for the person that's alphabetically the first last name. You take it out of your pile and you put it down. Then you look for in the remaining amount of pile you have, look for the person who's got the, you know, the last name that appears first. Then you put that on the pile. Now look through your pile again and look for the last name that appears first. Put it down, right? And you just keep doing that until you run out of papers, right? So it's a highly understandable one, right? It's understandable how to do that. We're just going to do it in place, okay? So I'm going to do it on the board first rather than going through the slides because I like the way I do it on the board. So let's see. Here. Whoops. Yeah, let's make everybody dizzy. Okay. So, the way I like to practice arrays, by the way, is I like to generate the numbers 1 through 8, and then what I'll do is I'll write them in order, but I'll put them in different places. So 1, 2, 3, 4, 5, 6, 7, and then 8. Okay? So we've got something that's sorted, right, like that. So the way selection sort works is that I look through, so I'm going to look through here, and I'm going to look for the smallest item. So 8 is currently the smallest, 2 is the smallest, 4 is the smallest, sorry, 2 is still the smallest, 2 is still the smallest, 1 is the smallest, and then I look through the elders, determine that 1 is the smallest thing I found. That's the smallest item. It needs to go in index 1. It's our index 0. So I swap 1 with whatever's there. So 1 and 8. Okay, so I just swap them. Okay, so now I've got this sorted portion of the array and I've got this unsorted portion of the array. So I look through the rest of the array, okay, that's unsorted. So 2 is the smallest, and then I look through all of them, determine if 2 is the smallest, and so I swap it with whatever's at index 1, which happens to be itself. Okay, understand it just swaps with itself. 4, 3, so 4 is the smallest and 3 is the smallest. We found 3, so we swap 3 and 4. Then we determine that we go through the rest of these, determine 4 is the smallest, so we swap that with 4 and 5. And we want to do these all in place, right? Because we want to, a lot of these algorithms we're going to do in place except for merge sort. Merge sort, we're going to say that that's left in place. Merge sort is left as an exercise to the insane. So, but all these are done in place, meaning we don't use any extra space except for what we have, except the, you know, a reference is worth of space to swap stuff. 8, 7, 5. So found 5. Then 6 is the next thing. And then 8 is, then we do 8 is small, 7 is small, swap it over there. And then when we get to the last one over here, we don't have to change anything, right? We don't, we get that one for 3. If you've got one item left, it's the smallest thing. We don't need to do anything with it. So let's just count how long this took. So to figure out what went over here in the first space, we had to check 8 items, right? Right? To check what went in the first space, we had to check 8 items, right? 1, 2, 3, 4, 5, 6, 7, 8. Then we had 7 items to check for the, then 6, then 5, then 4, then 3, then 2, and then, so 1, 2, 3, 4, 5, 6, 7, and then we said we got the last one for free, right? We kind of just get the last one for free. Right? But this is essentially, except for the 1, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up to n. Right? This is, you know, this is the classic n squared growth kind of deal. Right? If we had adding one more item to sort would mean that we have to do 9 more checks over here. Right? Adding one more item means that I have to do n amount more work. Right? As opposed to 1 amount more work. So this is a quadratic growth here. Now, the first 3 algorithms all have quadratic growth, but there's a reason why I'm going to say selection sort is the worst. So selection sort is very constant in the way it does, of what does this. Because if you've learned about Big O in previous classes, you probably learned about like just the worst case scenario. Here we're going to look about worst case, best, best, average, and worst cases. Okay. Worst case scenario for selection sort, everything's out of order. Okay, so like it's in reverse. Typically, like reverse is the worst case scenario. Right? Something like sorting a reversed array 8, 7, 6, 5, 4, 3, 2, 1. right? It's got to look through all the items, and it's got to look through the remaining items, and look through the remaining items. So it looks through all of them, and it runs that way. It does 8 checks, then 7 checks, then 6 checks, then 5 checks, then 4 checks, then 3, then 2, then 1. Right? Well, it skips that last one. But what about like something like where only one item is out of order with selection sort? Let's go with or 2 items rather are out of order, because you can't just have one out of order. 2, 1, 3, 4, 5, 6, 7, 8. So first thing we do is that we go through. So we look at 2, right? 2 is the smallest, 1 is the smallest. We eventually find 1 is the smallest, and then we swap 1 and 2, right? So we do 8 checks and then a swap to determine that 1 and 2 are that 1 needs to go where that is. And then the next thing we do is that we check 7. We check the next 7 items, 2 through 8. And we're going like 2 is the smallest. We go 3 is the smallest. And then we go. Basically, we do 8 checks and 7 checks and 6. It already sorted itself on the first go, right? But it has no way to detect that, right? In other words, it doesn't matter if it's like partially sorted. There's no way for it to short circuit. Furthermore, if I passed it this array, the sorted array, what's it going to do? It's going to sort the sorted array, and it's going to take O of n squared time. No matter what you do, best case, worst case, average case, it's always going to run exactly the same. Selection sort is always O of n time. That makes O of n squared time. That makes sense to everybody? Selection sort is terrible because there's no best case scenario. Everything's the worst case scenario. Okay. So, so again, what you do is you find the minimum, swap it, find the minimum, swap it, find the minimum, swap it. And then it just expands the code for you if you want to check it out, but it's not really too scary. So there are 2 different. Well, there's 2 different. So this is a bit of an important distinction. What I care about over here is that I've been counting the number of comparisons, which is the number of things that are checked, right? How many things am I checking to see in the smallest? I check all the items 8 times to check. Sorry, I check all 8 items to see which one's the smallest. Then I check 7 items to see which is the smallest. And then I check 6 items to see which is the smallest. So I do O of n squared checks. But there's another type of operation in there that we want to also count, which is the number of exchanges that they do. In other words, how many swaps do we do? And in selection sort, you go through, you find the smallest, and then you do 1 swap after you find the smallest. So each time you find the smallest, you do 1 swap. So finding the smallest takes O of n time, and then doing the swap is 1 step. Yes?
So why is it not n factorial?
And
we're doing like 1 less.
There are 2 different. Sorry, it's 1 less?
Like we're taking 1 less every time.
It's 5. It's because that would be times. 8 times, right? Yeah, 8 times 7 times 6 times 5, right? That's factorial. But we're looking at plus, right? We're doing 1 plus 2 plus 3 all the way up to n, which would be n squared, which is like n squared, right? It's that equation. It's n squared. N times n plus 1 over 2, right? So the exchanges, though, are something else we're going to check. So basically, it's very heavy on the comparisons, but very light on the exchanges, on the number of swaps you have to do. Each item gets swapped once. Now, this probably doesn't matter much because the way most computers work and the way objects work is that doing comparisons are much more expensive than than swapping 2 things, right? However, if swapping things were the expensive, if exchanging things were the expensive operation and comparisons for some reason were super cheap, then you might care about the exchanges. So that's just something to keep in mind. So selection sort isn't terrible if you care about the exchanges, but for our purposes, it's terrible. So let's learn about the bubble sort, which is surprisingly less terrible. So bubble sort is actually a really simple algorithm. It's also a quadratic sort, and what it does is that it looks at adjacent values in an array or a list. And then it exchanges them if they're out of order. So it just looks at pairs of values. It's called bubble sort because your smaller values, they bubble up. Well, sorry, that's the reverse way. The larger values bubble up and the smaller values sink. To the, let's go ahead and see what that looks like. Again, let's create an array over here. So this algorithm is much more interesting because there's actually some optimization we can do. Okay. So we've got, let's say, 1, 2, 3, 4, 5, 6, 7, and let's put that 8 between the 4 and the 5. Okay, so we're going to compare adjacent pairs of items and then swap them if they're out of order. So 2 and 3, are they out of order with comparison to each other? No. 3 and 6, they're not out of order. 1 and 6, however, are. So we're going to swap 1 and 6. 6 and 4, are those out of order? Yep. 4 should go before 6. What about 6 and 8? No. 8 and 5. Yeah. What about 8 and 7? Yeah. So notice what happened here. The value 8 kind of just, which is the biggest value I wrote down, kind of bubbled its way to the top. I'm going to enlarge. So 2, 3, 1, 4, 6. Right? It doesn't look too much sorted, but 7, by happy coincidence, 7 and 8 are already sorted. But the only thing we can guarantee that is sorted is 8. Okay? Right? We can guarantee that when we do this process, this compare adjacent items and then swap them, that if we do this, then the biggest item will get to the top. Why will the biggest item will get to the top? Well, a smaller item. So say you've got, well, what happened with 6? It went up until it hit an item bigger than it, which was 8, and then it moved forward, and then 8 was checking the smaller items. So essentially, if you've got the biggest item somewhere, it's going to be bigger than everything else, so it's going to swap with everything until it gets to the top. So the biggest item will always bubble its way to the top. You could also go from the reverse with the smallest items, but traditionally this is the way this is done. Of course, we're not done yet, so now we have to look, we just continue. 2 and 3 are not out of order, but 3 and 1 are. So swap 3 and 1. 3 and 4 are not out of order, 4 and 6 are not, 5 and 6 are. Oh, this is starting to look way more sorted. 6 and 7, 7 and 8. Right, we don't have to check 7 and 8 though because we knew 8 was already sorted. So now we know this amount is sorted, right? So we could do this again. 2 and 1, 2 versus 1, that's out of order. 2 and 3, 3 and 4, 4 and 5, 5 and 6. So we know this amount is sorted. Then check 1, 2, 2, 3, 3, 4. So we know this was sorted. 1, 2, 2, 3, 3, 4. So we know this is sorted, and so on and so forth, right? Of course, it was sorted a while ago, and I'm just running the algorithm again and again, right? So, so there's actually a way we can short circuit this, though, which is that saying that basically that we can, that if we just do this, okay? And if we get to an iteration where we didn't have a swap at all, we get to basically, we're over here, right? And we did the swap for 1 and 2. So now we did a swap this time, so we're going to go through and do our algorithm again. So now we compare 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 7, 7 and 8. And we notice we didn't do a swap this algorithm. Well, if we didn't do a swap, that meant that nothing was out of order. So we can just stop. It's sorted. So we can essentially have a fail-safe in there that if we get past the sorted array now, we go through it once, you can see that nothing's out of order because there were no swaps, and we just return the array. So best case scenario for bubble sort is actually pretty good. Best case scenario is O of n because we get past it. Best case scenario, we get past the sorted array, and we do it, and we don't do any swaps, and we go, oh, we're done. Okay. What about worst case scenario though? Worst case scenario for everything is pretty much is the array in reverse. 8, 7, 6, 5, 4, 3, 2, 1. And this one's pretty easy to see what's going to happen here. 8 is going to swap with 7, and 6, and 5, and 4, and 3, then 2, then 1. So first pass through the array, it's going to look like this because 8's going to swap with everything. Then 7's going to swap with everything and end up over here. Then 6 is going to swap with everything and end up in that tiny little space between 1 and 7, right? And so on and so forth until it's sorted, right? So it's going to take, we're going to check 8 items, then 7, then 6, then 5, then 4, then 3, then 2, then, well, the last item's free again. So that's O of n squared, right? So best case scenario, O of n. Worst, O of n squared. And on average, of course, the average is actually going to be most like except for quick sort, the average is going to be the worst case as well. So its average case is also O of n squared, because most arrays are going to be something that's out of order and it's going to look somewhere like quadratic time, where it's going to be like n squared divided by 2 because you can stop halfway through, but it's still like O of n squared. But what about the tricky function that I passed in earlier, where only one item is sorted, right? Because a lot of times, if you're sorting data, only a bit of the data might be unsorted. 3, so something like 1, 3, 2, 4, 5, 6, all the way up to like, 1 million, right? All numbers from 1 to 1 million, right? For selection sort, what we said would happen is that we would check 1, right? We would find what goes in spot 1, then we'd find what goes in spot 2, then we'd find what would go in spot 3. So basically, you do 1,000,000 checks, then 999,999 checks, and then 999,998. So it'd take O of n squared. But bubble sort, if we're doing this, we check 1 versus 3. They're not out of order. 3 and 2 are out of order, so we swap them. And that sorts it. So we continue doing all the rest without swapping. But we swap something, so we do another pass, right? And then we do our second pass, and we didn't swap anything. So on our second pass, we realize we can stop. So if like only one item's out of order, instead of doing O of n squared time, we did something much closer to like O of n, because we did like 2n checks there. So bubble sort's actually quite good if you've got that that failsafe in there. So do for each pair of values, if they're out of order, swap them. And then, if they're out of order, for each pair, if they're out of order, swap them. And now, where double sort can be worse than selection sort is the number of exchanges, right? You're guaranteed that each item is only going to exchange once. In selection sort, right? You just simply find the smallest and swap it into the appropriate space. With bubble sort, right, if you've got that reverse array again, if we've got 8, 7, 6, all the way to 1, well, 8 is going to swap n times, then 7 is going to swap n minus 1 times, and then 6 is going to swap, 6 is going to swap 5 times, and so on and so forth. It's going to swap basically worst case scenario is O of n squared exchanges. But again, exchanges are cheap compared to comparing items, typically. So the end result, though, is that basically, kind of summarizing what you might intuitively be thinking here. Bubble sort's great on stuff that is pretty much almost already sorted. Like if it's almost already sorted, bubble sort's actually a pretty good sorting algorithm because it's gonna finish quickly. But if it's an inverted array where basically everything's reversed, right, which is the typical worst case scenario I've given for everything, that's when it's going to do the worst here. And this best case scenario of O of n time for a lot of arrays is why we even bother looking at basically some of the easier sorting algorithms, because stuff like merge sort is always going to run n log n time. But sometimes it's better to combine that with a better algorithm to get, worse algorithm to get maybe a better time depending on how things work. So now to go on to insertion sort, which is my favorite sorting algorithm because it sounds a lot like selection sort, but and bubble sort, but sorry, you confuse it with selection sort because of the name, and you might confuse it with bubble sort because of how it works, but it actually works in a subtle way that's very different, and it's very powerful. It's kind of also the way you naturally sort stuff if you're playing with cards, right? The idea here is when you're like playing cards and you get a new card and you want things sorted, you'll insert it into the appropriate place. So when you draw a new card, you'll have your cards which are already sorted, and you'll insert it into the sorted place. And that's kind of the algorithm we use here. We're going to split the array into 2 portions. Okay? Split the array into 2 portions. Right, we'll have a long, nice big array, and we'll split it, we'll have this area which is sorted. Right, so we'll have the sorted portion of the array, and then we'll have the unsorted. And what we're going to do is we're going to take each item from the unsorted portion and put it into the sorted portion. And so that it's going to remain, we're going to put it into the proper place in the sorted array. And what this does, this small subtlety, it actually has huge implications. Also, it's now time to talk about how much I love Wikipedia, especially for sorting algorithms, unlike other professors in your liberal arts, because the reason they mainly hate Wikipedia is not because of Wikipedia itself, but because of the students who cheat and are terrible at cheating, who will copy and paste wholesale from Wikipedia, or even worse, or sorry, not worse than copying and pasting, but also just as annoying, but also an annoyance, citing Wikipedia. You don't cite Wikipedia because it can change, number one, and 2, it's a tertiary source, which is not appropriate for any kind of academic thing, right? It's a summary of other stuff. It's an encyclopedia. You don't cite encyclopedias. You cite not even Encyclopedia Britannica. You would be citing. I mean, yeah, if they could teach you how to do that, but it's easier to hate on it because a lot of students don't understand the subtleties.
Yeah. Just go to the bottom.
Right. Right. Exactly. Right. And once you get into the higher level stuff, you go, okay, you go scholar.google.com, and then you log in and you go, okay, and then you start looking for more primary sources or secondary sources, right, in here. So nice thing about here. So if you're looking for binary, if you're trying to do a paper for some reason on binary search trees, right? You can find, things here. You can find your sources, but also what I like about this is that, of course, that it automatically generates the what you need in the appropriate format. I do everything in LaTeX, so I will do it for BibTeX. Oh, there's Knuth again, right? Told you he shows up everywhere. Okay. Anyway, so back to why I love Wikipedia. Because their sorting algorithms are great. So let's go to bubble sort. Okay. So that image doesn't necessarily mean much to you. It's a static visualization of the sorting algorithm. That never did much for me. The GIFs, on the other hand, are GIFs. These do it for me, where basically it will compare stuff and swap them and show you how it works. Let's look at 6 and 3. They're out of order, so we swap them, right? Kind of deal. So these are nice visualizations. Here's kind of a visualization of how bubble sort works with where basically we continuously swap stuff. So there's a lot of nice visualizations that are on Wikipedia, and then it's got a nice selection of all the other algorithms here. Selection sort, it does, but insertion sort I like. But here's selection sort, right? It's just grabbing the smallest dot and swapping it with the thing already there. And then it also has its stats over here. So what insertion sort looks like is that, notice that basically that it's just taking an item and it's inserting it into the place in the appropriate place in the array as it's going. Right? It's going to take this item and just slowly move its way down. And until the entire thing is actually sorted. So why am I talking about this? implementation, you get there's a 3-line there's a 3-line C version and a 5-line optimized version. And I mean, but in C everything's 1 line if you try really hard. It's very efficient on small data sets. So if you're talking like 64, if you're talking like a set of like 64 or 128 or something like that, it actually works blazingly fast. Like 64 times 64 isn't that big. 120, 128, that's kind of big, but 64 by 64 is really small. It's much more efficient than selection sort or bubble sort. It's adaptive. In other words, it's really good for stuff that's already partially sorted. It's even better than bubble sort for partially sorted stuff. It's stable, meaning that if you have 2 things that have the same value, say you have like the Queen of Hearts and you have the Queen of Hearts and you have the Queen of Spades in your input, right? Then the output will have the Queen of Hearts, then the Queen of Spades, right? It's not going to go Queen of Spades, Queen of Hearts. So if it showed its way inside, so basically if you have 2 items with the same value in the input, they'll be in the same order in the output. So that's kind of useful. In place doesn't require extra memory, and my personal favorite thing, it's online. In other words, you can say, oh wait, I forgot half the data you need to sort. All the other sorting algorithms we're going to learn this in the next couple of lectures. If you do that, it's going to have to start over. Insertion sort, you can give it more data because it's got the whole sorted, unsorted piles. You're just adding more to the unsorted pile. You're not affecting the sorted pile at all. So you're not going to affect the work that's already been done. So insertion sort is pretty cool. So how does insertion sort work? Well, we're going to just simply create a sorted and unsorted portion, and we are just going to, work with it that way. So let's go with 2, 5, 4, 6, 1, 3, 7, and then 8. Okay, so let me rewrite this a bit to make it fit. So 2, 5, 3, 4, 6, 8, 1, 7. Okay, so to sort, so with insertion sort, what we need to do is we need to separate this into a sorted portion and an unsorted portion. Okay, so pro tip. Sorted arrays of size 1 are sorted. So now I've got a sorted section and an unsorted section, right? Make sense? I've just simply declared that the first item is sorted and that everything 5 and beyond is unsorted. Right, so now here you're going to see why insertion sort is fantastic. So let's now move this and say let's insert 5 into, let's basically put 5 into here and adjust the sorted portion so it's sorted. Well, it didn't need any adjustment because 2 then 5, it's sorted, right? So now let's look at 3. So we're going to essentially push down 3 into the sorted portion of the array until it's all sorted. So 3 compared to 5, that's not sorted. So we swap 3 and 5. Then compare 3 to 2. Well, 3 to 2, 3 and 2 and 3 are in order over here, right? 3 is not smaller than 2, so we can stop here. Why can we stop? Well, because if there's stuff in front of 2, since we assume this is sorted, anything in front of 2 is going to be like a 1 or a 0 or something negative. 3 is definitely going to be smaller than those things, so we can just stop here. Okay, 4. So we've got this sorted portion, we've got this unsorted portion. So now we're gonna push 4 in. 4, 5, and 4. 4 is smaller than 5, so we swap them. 4 to 3 compared to 3. 4 is smaller. 4 is bigger than 3, so we stop here. We don't need to push it any further down into the array. Okay. So we've got our sorted portion and our unsorted portion. This making sense so far to everybody? Now we've got 6. Well, now we're going to push 6 down into the array. 6 is greater than 5, so don't do anything. 8 is greater than 6, so don't need to do anything there. 1 needs to swap with 8, then needs to swap with 6, then 5, then 4, then 3, then 2, then 1, right? So we got to swap with everything to push 1 in, right? So 1 swaps with 8, then 6, then 5, then 4, then 3, then 2, then 1. Sorry, just 1 doesn't swap, so swaps with 2, and then so it's at the beginning now. So because it hit the beginning, there's nothing else to check, so it stops. Now 7. 7 compared to 8. Well, we swap 7 and 8. 7 compared to 6. 6 is smaller than 7, so we stop pushing 7 in. So this is insertion sort. And notice we got basically a bunch of freebies, essentially, where we said, let's insert this item into the sorted array. Oh, it's bigger than everything in the array, so job done. Or we pushed it in like 2 steps, and then it was done. So it's actually pretty good for that. Worst case scenario, though, for like the reversed array, right? You've got it still performs just as bad as the others, like 8, 7, 6, 5, 4, 3, 2, 1. Well, what are you doing? Well, 8's already sorted. Then we push 7 in beginning, so we swap 7 and 8. This is the sorted portion. Then 6 is going to have to swap with 8 and then 7. Then 5 is going to have to swap with 8 and 7 then 6, and so on and so forth, right? So worst case scenario, though, with the reversed array, you're still looking at O of n squared time. Best case scenario, though, you're doing a single pass through the array, just like bubble sorting. Right? If you're given a sorted array, insert insert 2 into the sorted array, insert 3, insert 4, insert 5, insert 6, insert 7, insert 8. No real changes are needed here. It's very, very simple, very, very powerful. Let's see the slides in the last 5 minutes. So here we need to insert 25. Swap 25 and 30, and then it's done. Insert 15 into here, so we swap with 30, then with 25. Insert 20. 20 will swap with 30 and 25 again, and then 28 will swap with just 30. Essentially, and here is like the actual kind of code that it uses, the pseudocode, where essentially it's just essentially copying stuff over, but it works really well. And again, it's O of n squared for the comparisons, but it works really, really quick. There's a lot of actually like, and when you're not dealing with the worst case, there's a lot of like 3 steps you can get. People are looked to be gearing up to go, so I think I'll go ahead and since we have 4 minutes left, I think I'll cut off the lecture here. Then on Wednesday, I'll go over a review for the exam, and then we'll resume on Monday. And then let's see. Then when's the last day of class? Anybody know? Is it the 30th or the 7th? 30th. So we have plenty of time on Monday to go and Wednesday to go over the stuff, and then 2 more weeks to do graphs, and that's plenty.